So welcome to this FEFLOW webinar. As you know, every month we run a different webinar related to groundwater modeling, geothermal, and groundwater contaminant transport using FEFLOW. Today, the webinar is related to a new module it complements our FEFLOW programming interface. This is called PySMH. We will do a lot of Python scripting today. If you would like to have a copy of the script, so you are very welcome to send me an email and I will reply you with a copy of the script. So today's presentation has the following agenda. So we will start with some introduction about FEFLOW and some announcements. So then we will talk about the FEFLOW programming interface. And at the end, I will have 2 demonstration exercises. Okay, announcements. So we have our FEFLOW International Conference. This will take place in Hamburg, Germany from the 8th to 11th of October. We have been receiving a number of scientific contributions. So if you would like to send your abstract, please go to this website and then take a look at different instructions. I'm very welcome to contribute. So we are having multiple sessions related to groundwater modeling, geothermal applications, uncertainty quantifications, implicit modeling, conceptual modeling. So we will see a lot of topics related to 3D and structure meshes and how to integrate this into FEFLOW. And so if you are interested in contribute also about groundwater and surface water interaction, so we will have a dedicated session about that topic. Okay, we keep developing a number of free training courses. So I give you here the overview of the different courses that we have. If you are new to FEFLOW, you will see a course related to getting started with groundwater modeling. This will give you an overview how to operate with a graphical interface. Recently, we published a new course called FEFLOW Behind the Flow, which it's focused on the theoretical part, how to solve the groundwater flow equation in FEFLOW. We have a course related to groundwater quality, heat transport for open loop and closed loop systems, and also for advancing modeling of complex geological structures using our 3D modeling modules. Today's webinar goes about Python interface. So we also have 3 courses about this. The first one is getting started with FEFLOW-Python interface. Today, I will basically discuss about this third module called FEFLOW-PySMH. If you are a FEFLOW user and you have a FEFLOW valid SMA, you are granted to the option in the middle, where is give you additional hints about FEFLOW and Python interface. These courses comes with a lot of material, so you can always download the material. If you're interested in FEFLOW-Python interface, you can go to the courses and just download the scripts, and this will help you a lot to get started with this. Okay, for those ones new to FEFLOW, so FEFLOW is a finite element software and can do a lot of groundwater processes from flow, contaminant transport, reactive transport, groundwater age, heat transport under fully and variable saturated conditions. So FEFLOW is a software which exists already from the late 70s and is being in continuous development by DHI. We will have a new release now coming by the beginning of May, and a major release coming in November. So for those coming to the FEFLOW conference in October, you will see a significant number of improvements in the new version of the software. Our main course is, so we see the software as all-in-one solution. So DHI is not just a company dedicated to develop graphical interfaces. So we develop the engine, so the numerical part of the software and the graphical interface. This gives us a full flexibility to decide what do we want to develop and when do we want to develop, so we can optimize the software at maximum. We spend a lot of time in improving workflows to save you time and also boost different efficiencies in groundwater modeling. Specifically today, we will be focusing on that with our Python Python interface. And we have a lot of methods for visualization in 2D and 3D, which makes FEFLOW graphical interface industry leader in visualization for groundwater modeling. So FEFLOW main concept is you do everything in one single file. Either it's a simple box model or something more complex. You can work in multi-scales from local to regional. One project, one file, so don't need to mess up with different text files. And you have also one graphical interface will allow you to control all the different processes from one location. At the same time, we cover through our workflow from model conceptualization. This is something that we have been developing since the last years, and this year we will be more in conceptualization in 3D coming later with FEFLOW. We do a lot of meshes in 2D and 3D, tetrahedral meshes directly in FEFLOW. The whole simulation, calibration, and predictive uncertainty quantification can be also carried out with the software. Okay, so let's go to today's webinar topic is about how to improve the modeling workflows using the FEFLOW and Python interface. So we have a programming interface. This programming interface exists already since more than 20 years. So, it was originally based on C++, but since almost 10 years plus is working with the FEFLOW and Python interface. The FEFLOW programming interface, so IFM interface manager, is extensive documented. So we have an online help, Git repository where you can see what the full documentation of the different methods with examples. And of course, the self-paced courses are a good option to learn the FEFLOW programming interface. Okay, so why do we need this? Because we can automatize a lot of the workflow, so pre-processing and post-processing. It was, since many years, always the possibility to control parameters, so set parameters, create boundary conditions, or extract information, but it was not possible to create meshes. This is something that we implemented the last year in the last release. So now you have, with one single Python script, the whole workflow from model conceptualization, mesh generation in 2D, 3D, parametrization, and post-processing. And of course, you can also use this programming interface to extend the capabilities of the software. There are some users who has been developed plugins or scripts to incorporate different physical processes on top of what FEFLOW can offer you today. As mentioned, so we have a Python binding and C++ connection. They have different pros and cons depending on the type of application that you would like to do. To give you an example, so when will you go for Python is if you want to do file operations. So you will, for example, would like to open a file, save, run, or if you have many FEFLOW documents, so you will manipulate the different FEFLOW documents. You can control licensings and others. In C++, you don't do file operations because the plugin, the compile library is attached to one single document. But it has the advantages because C++ is more is a language which is more powerful in terms of performance, can do a high-level computational calculation. So if you need those ones. There are a number of functions to manipulate. So we call kernel functions for Python only, so as mentioned, to manipulate the documents, to access results. So our results are saved in the DAG file. So the DAG file contains a number of time steps. So you can basically load the DAG file and ask, give me this specific time so that you don't need to load exactly the entire full document. It's really quite efficient. We also have model functions, which are available in both Python and C++. So if you would like to control properties depending or based on elemental information or nodal information, like boundary conditions, you can do it in both cases. If you would like to manipulate time series or create time series, maybe you would like to interpolate values in between time series or create your own charts, calculate budgets, and selections, manipulate selections, or control the numerical settings used for the calculation. So these are options available in both methods, Python and C++. But we will be talking today about Python, so let me start moving in this direction. So FEFLOW and Python interface. So to start with the demonstration, I need to give you some introduction, how to use it. First of all, you need to have installation of this package, comes with a FEFLOW installation. You need obviously Python. I didn't put it here, but you need Python as well. And later you will see that if you want, you need also Python interpreter. How do we call FEFLOW, or how do we connect FEFLOW with a script? There are many ways. You can have a script, a Python script, which is the master, and the master will call the subprocess FEFLOW. So it's typically when you do pre and post processing. So you would like to prepare a number of parameters or change parameters, or you have already a DAG file with results. So you will have a script to access the FEFLOW document and extract data or put data into the document. Or the other way around. So you could have FEFLOW as a main process, and in FEFLOW, in the FEFLOW document, in the .fem, there is a Python script embedded. This is applicable in cases where you would like to do something in parallel with a calculation. So if you would like to, I don't know, change some boundary conditions depending on some response of the simulation, then you can have this script inside the FEM file. So it's quite nice as well because it's portable. So you need to just carry one FEFLOW document, and the script part will be stored in our file. Depending on the documents that you operate, there are methods accessible. I was talking before about FEM documents and DAG documents results. So there are different methods, and just give you here a quick overview how to what is possible. So if you have a document, a FEM document, you can start the simulator. You can pause the simulation or stop the simulation. You could submit changes which are pending. So you have been doing some changes in the document, and you want to make sure that has been passed forward to the FEFLOW, then you can submit this. If you already have a result file, a DAG file, then you would be able to get how many time steps you have, and you will also be able to load specific time steps. So if you know how many time steps you have and what are the times where you calculate, you can ask FEFLOW, give me the results at time steps corresponding to 120 days. And then for both documents, so you can control licenses, open the document, save the document, so as you like. So that's our generic methods. Okay, so functions, because you need to do a lot of things to manipulate, to access data. Normally you do it through IDs of nodes. It's a node number or elemental number. There are a number of layers, number of slices. So there are functions to get this basic information, like how many dimensions has the problem. So if my model is 2D or 3D, how many layers I have, slices, nodes, so that you can loop and iterate through different methods to get information. So if you got the node, so you can ask, give me the coordinates of the nodes, or give me the nodes connected to a specific element. So this could be get number of node elements or get the element. You can get geometrical information like coordinates, the extent, the origin. You can change values of these geometries, so change the elevation, for example. You can find nodes. So if you are importing a shed file with points containing wells, I will do it in the exercise. And then you can say, okay, find me the next closest FEFLOW node given XYZ, so that I can put my well BC in this location. You can set parameters or get parameters in one single line. So you can say, get parameters, give me the entire groundwater recharge, and then you get as a result a Python list with all the different parameters organized according to the node number or elemental number. In other cases, it's necessary to compare multiple documents. So if you are doing some sensitivity analysis, you can take advantage of the multi-document operations of FEFLOW. So you can create a number of documents. So load document 1 and document 2, load the document, and then you compare between the documents or extract results, and then maybe put some data from one document to another. So that is the typical operations. Here, I summarize all the different ways to connect FEFLOW and Python. So if you have a FEFLOW installation, you have the GUI, and from the GUI, there is a scripting panel where you can attach your script, write your script, and do some operations directly in FEFLOW. If you like to work with Jupyter Notebooks or with other scripts or through external interfaces, you can also do it. It's not limited. If you call the FEFLOW console, so you call FEFLOW 81c.exe minus Python, will initialize the Python installation. It comes also with FEFLOW tiny Python installation, so that you can also run some Python commands through the FEFLOW console run. That's quite interesting. When you run the model, sometimes you would like to interact with the simulator during the run. So if you want to change maybe parameters dynamically based on certain conditions, so you can set parameters before the flow equations are solved if you are talking about hydraulic parameters. So you can access these methods through callbacks and say, I would like to do something pre-flow simulation, or I would like to change the conductivity before the time step is being executed. So then there is a callback called pre-time step. So then you change your parameters, then you leave it, and then FEFLOW move to the next step, and then use the new values of hydraulic conductivity to solve the time step. So this is the overview of the different callbacks, and we can access methods for flow simulation, mass simulation, and heat simulation. So you can change things before or after. So if you are doing some post-processing, obviously it makes sense to do it afterwards. So you can do afterwards every equation has been solved, or you can do it after the time step has been completed. So if you're doing a flow, mass, and heat simulation, the best location will be as the post-time step, for example, to extract it. And every parameter in FEFLOW, every single detail that you will see in the GUI, so if you are setting your problem class to confined or recharge, or even if you use phreatic and then define the number of slices and which slice has certain properties, every single detail has a name in the Python interface, has a constant, which is ID or a name. And there is a list of these enumerators through our submodule called enum. And this is interesting to know because it's easy to operate knowing these constants. I will show you a trick how to get access to those in parameters. And of course, we keep developing more and more. So what I would like to focus today, basically in this webinar, is about this new interface, what we call it PySMH. PySMH is an advanced layer on top of the IFM module. These allow you to manipulate, to create, edit supermeshes. So if you have a supermesh, then obviously you need to call the mesh generator. So we can call the mesh generator. You can define the number of slices, change the elevation, call interpolator method, set parameters with lookup tables, and extend the model in 3D. So basically, this covers everything that you require to build a FEFLOW FEM document. On top of that, many people started asking, and also in the HI internally, we needed the possibility to create cross sections directly with FEFLOW. So how FEFLOW operates in the graphical interface? Quite simple. So you basically create a polylines, and these polylines you can ask the software build a cross section. When we do this in the graphical interface, basically we create a pseudo mesh in 2D. And we do the same now in Python. So you can pass a line or a plane, and then we create a new 2D mesh from that. And in this new mesh, which is 2D, representing the cross-section, you can apply any of the existing IFM methods. So you can ask, give me the conductivity or the hydraulic head at the nodes in this cross-section. And this facilitates a lot the visualizations and the control, especially in 3D full structure models, because you can draw arbitrary number of polylines, and through Python verify a lot of the information that you assign into the model. Right, and with this, I would like to move to the live demonstration. So for the live demonstration, I have two examples. So I'll try to scripts in parallel. I mean, I have already the scripts prepared because I don't want to waste time writing the whole. So in the first one is what we will do is we will have, it's called build geothermal. So we're going to build an entire geothermal model from scratch. There's nothing, and the only thing that I need are the dimensions of the domain and the locations of the wells. For we will have a geothermal doublet, so one injection and one production well. So to give me a second to start, I just need to close a few windows here. Okay, so to start, we need basically to define the FEFLOW library. So it's called IFM, and then you import the constant with these methods from IFM import enum. And then I'll just need to put some paths, so which is nothing complicated. So I have a script somewhere, save, and just go into a location where I will put the Supermesh file. I will create a steady state file. I will later create a transient FEM, run the simulation. So I need to have a DAC file, and I have some data, especially for the topography, or only the topography in the import export. I always like to use this line here because I have a lot of multiple installations on FEFLOW and basically want to know what is the FEFLOW version being used. Okay, so how do we start? Basically, you need to create the Supermesh. That's the method to create the Supermesh. So if we run it and then we print it, so you can see that there will be an empty sun running FEFLOW 1, update 3. This is the one that's gonna come now in May. So I have a Supermesh objects. This object has no extension and has nothing because I didn't initialize the whole geometry. So what we recommend you is that from the very beginning, you define what you want to do with the software. This is also some extension that we include since the version 7.5. At the Supermesh level, you can say, I would like to set my problem class. So there is a class called problem definition, it's also documented. And I'm saying I would like to have a heat simulation, heat transport. These are the name of the variables. It's a steady state and it's a saturated system. Yep. So that's the definition. Then I would like to start ending some reference system. So we will have a origin. So this origin is optional. I have the origin because the box has a dimension of 7 by 7 kilometers. So just to keep the coordinate simple, I use a origin. And the first step is this is my Supermesh object. I need to start adding information to this. And the information that will be added are polygons, lines, or points. This is the basic, the primitives that you include. Then on top of that, you can have a hierarchy level, something that is called compound. You can create a compound element, which can be a group of polygons, a group of lines, or a group of points. And with this, I create elements, which is a polygon, and it has the dimensions of 7 by 7 kilometers. Here you need to be careful with the way how you type the units. It needs to have an order, it's counterclockwise. And basically, that's if you follow this rule, it's very simple to start developing. Okay, so this is my polygon. I would like to add some points. So I have 2 points. So one is for the injection and the other is for the production borehole. And I would like to control the mesh around these points. So for this, I will use auxiliary points, which I have previously calculated the coordinates of these points. So you can do it directly in Python or in Excel as you like. And these are this. So we have another number of points. So we have 2 points for the wells, and I have 12 points that are around this borehole. So I would like to control the discretization. So let's try to now save the Supermesh and see what we are doing. So I'm just gonna save the document. And the document is gonna be called PySMH. If we run this, and to open FEFLOW, of course, I could display the mesh here as well, but I need to write more lines for that, and to not make it too extensive the script, I just open FEFLOW to visualize. So I just load the, no, it's not this, um, we, here we go to the Supermesh, then that's the time, it's now, so 4:28. It's the time in Berlin, and I see the box with the dimensions that I specify. Then we have in the middle the borehole, and I'm adding 6 nodes or 6 points around. So I could stop here and then create a mesh and then do the rest as usual, but that will not be what we want to achieve in this demonstration. So what we want to do now is to set the elevation. So we know this model will be a 3D model, and for this I need to define some elevation settings. So we just say, okay, we want to use an interpolator. That's nice because I don't need to implement the interpolation in Python or use a package. I can just say, I would like to use FEFLOW regionalization method for using invert distance. And I can control any property of the mesh of the interpolator, like for example, the number of neighbors. There are more properties, but I just pick the ones that I want to use. All the others are defaults. And then the rest is adding the slices. So you need to have an idea how many slices or layers you need depending on your conceptual model. So in my case, I have these ones. The method is so straightforward, is say add a slice, and add a slice can be added using elevation data. So you have external file. This file is under my import export folder, and there is something called topography, and telling FEFLOW use this interpolator regio and use these columns to do the interpolation. That's it. And then I can tell when the layer slice 1 is interpolating using the points from this topography.dat. Add a slice exactly 50 meters below, 100, 150, and so on. And keep doing this. And at the end, I will have one slice with a constant elevation of minus 1,000 meters. So that's if you can see the elevation is basically a deep geothermal example, what we are building here. So if we run this, it's gonna take just a second. It's done. And now if I just reload the file, then you can see that the information here is, if you go to the meshing panel, this information is already set here. So if you press generate mesh, FEFLOW is going to build a full 3D model directly from the GUI. But as I say, we want to do it from Python, so we just go back. So we have the elevation now set, and the next step is we need a mesh generator. And this just mesh generator is straightforward. So you say, again, Supermesh object and get the mesh generator, and you get access to all the FEFLOW mesh generators and using Triangle. So compared to other Python packages that you might know, so here you don't need to do any installation of Triangle. So we just basically use what is available in FEFLOW with one single line. From this, then you need generator properties, and these generator properties are the same properties, the same names, what you will see in the GUI. So you need refine points. I have some geothermal boreholes. I have a gradation of the points, and I have the size of the points, 25 meters. So with this, I cover the part of one is here. If I switch in the GUI to these parameters, basically are the ones that I'm controlling now in Python. And What else? We typically define the number of elements that we want to use. And for that, we need a so-called root element, so it's the uppermost level of the whole supermesh structure. Get root element, and then I'm telling that this root, so the whole supermesh will use this mesh generator triangle with all these settings, and I'm proposing 5,000 elements. And at the end, I just say generate the mesh. Generate the mesh, and to see the mesh, we need to save the FEFLOW documents. Otherwise, we will save only the, let's put it here, and then let's call here this one print. So saving fem, and I have a fem for the state, so still is nothing. So let's run this, and then you will see what's happening. What's happening in the console. There is a warning, and this is something that I did actually in purpose to demonstrate what's happened if you have intersection of slices due to the elevation that you pass. So we set a minimum distance. So this distance for now is fixed. You cannot modify it, but it's something that we are going to include in the next version. And now, and the mesh is basically ready. So if we go to the FEFLOW folder, so that's not the one that I want to. Yeah, here I call this one, so it's the time from today. And we can see now we build the model. We have discretized the 2 points, and we have the elevation. So the details, how the model was created, still in the meshing panel, and the different layers. See, if I go to the problem settings in FEFLOW, problem class, I see that I have standard, exactly what I indicate, saturated groundwater flow, heat transport, and steady state. So far it's working, this script. So we can keep extending this. And this time we need to change some properties. I I I will not do some fancy changes of properties because this is something that is already exists in the software since, as I was saying, 20 years. So I wanna just concentrate in the major workflows now with this new package. So I'm setting conductivity with one single line, and say all the whole conductivity will be these values in X, Y, and Z. Then I like to set some boundary conditions. And so what I'm assuming is that there is a geothermal gradients changing over specific depth. And for this, I need to know the nodes on the top of this of the model domain and on the bottom of the model domain. It's quite easy to get this. So I will, for example, need to know how many nodes I have per slice. So this give me the number of nodes per slice. And since I need to go downward, I need to know how many slices I have, get the number of slices. And using a Python loop for, we can go from the number of nodes, per slice. This is the slice number 1. And basically I'm telling, put a boundary condition for the heat transport of first kind. So this is a Dirichlet boundary condition. So I'm fixing the temperature with a value of 10 degrees Celsius. And I do the same for the lowest slice. And again, fixed temperature, but this time I have some increase in the temperature due to the gradient. So this is some simplification that I'm doing. Okay, so with this, I'm done with the heat. So we can call this heat boundaries, heat BCs. And then I need to have some flow. That's not a good idea. So flow boundary conditions. And for the flow boundary conditions, what we are assuming, because we are simulating 1 kilometer depth, a confined system, I'm taking the assumption that the whole system is confined. And there is an interesting only in the lower part of the geothermal reservoir. So the upper aquifer, the first meter is not relevant for me. So I'm fixing this to a constant hydraulic head, uh, which is making the model confined. So I'm just setting the values of this time is the boundary for the flow, first time, for each of the nodes, which are inside the slice number 1, with a value of 3,000. That's 3,000 meters above the sea level. That's with that and simulate and fixing the boundaries. And then what else we need? Because we want to get the steady state solution first. So we get the solver setting. Then I need to have some to run the simulation. I need to run the simulation, start the simulator. We save it. So we will save with the results and we stop the simulator. So if we run it this, it's going to take just a couple of seconds. So I use the time to answer, is the APIs publicly available for this advanced FEFLOW version? Yes, you can access this documentation, is public available. For the construction of the Supermesh, because it's something more advanced, so what we have decided is that users with a valid SMH and FM3, FMH3, and FH3 are granted to this package. So if you have any question, just say, I will give you my email address and then clarify. Okay, now the simulation is done. So if we reload this file, we should see in the temperature distribution in the model. So now we have solved with add that geothermal gradient into the system. Okay, so that is the first part of the exercise. So the second part is, okay, what is if you would like to change the model to transient? That's that again, you have a method to change the problem class, and this time the problem class will be unsteady, will be transient. And of course, you need to define the final simulation time. So we are saying that we would like to simulate 30 years. And I do the next part a little bit fast because we need to move to the other example, which is a bit more interesting, using more complex geometries. For the last part here, what I'm doing is I'm creating geothermal wells. So there is a method called create well manager, which allows you to create any type of well for flow, mass, or heat. So I'm creating multi-layer wells, and I'm putting one as injection, is a negative, and the second one is a abstraction. And at the end, I'm saving the document and starting the simulation. So let's start the simulation, and then in parallel, I will start opening another FEFLOW, another Python script, and we'll call demo 2. Okay, so simulation is, for this example, I need, in a second. So in the next example, what we are going to do in the last minutes is basically, we're going to construct a model using a external shed file. So I need this time few additional packages. So to visualize the polygons, I'm gonna show you here now how the polygon looks like, or the model area. So we have a shed file which contains the model area. It's model area underscore shape. This is not a FEFLOW method. This I'm using GeoPandas to basically read the shed file, and then display the shed file. So this is basically the model area that we want to include. So if you have done the introduction to FEFLOW, you will recognize this. So I'm trying to do via Python a part of the introductory exercise. Okay, so these lines are not anymore relevant, so we can even just delete them. So we have this. How do you build this geometry into into FEFLOW. I mean, the most, I wouldn't say tricky, but the most lines that you need to do here is basically how to extract the information from the shapefile using GeoPandas. So this is the model area. It has a geometry. So if you see here, this is the table. This is a column called geometry, and this contains the vertices of each of the 5 polygons. So I'm extracting all the geometry. Basically, I'm extracting the vertices because if you remember the example here, we need to know the vertices, not these ones, of the polygon. So you need to know the X and Y offset if you're doing 3D of the polygon. That's the whole job of this part of the script. And then uh, when I create a super mesh, I create now an element, and this element is the compose element. It will contain a number of different polygons. Basically, I'm adding each polygon here, each polygon and the coordinates into the super mesh. Polygons can also have properties, and these properties will be mm, be the mesh density, for example. So we can define the mesh density in each of the polygons. So I'm gonna just say save the polygon, say the super mesh, and see what happened. So we can open this one is not a file that I want. Super mesh. This one groundwater moon. And now I have the super mesh created. There is nothing defined because I haven't set any setting. So with this, I have the super mesh inside the model area inside the super mesh. We have some points because these points will be part of the super mesh. So let's add the points. Again, I'm reading the shapefile, extracting the geometry of the shapefile. It happens that the shapefile has some additional columns. One of these is names. So I would like to know what are the names of the wells. And then I start adding in the super mesh. So I put the information in the dictionary because I can use it later. And the FEFLOW part is basically only these 2 lines. You need to add the element, which is a point, the coordinates of the point, and then you can set the property, and you can pass the name. So if we run this again, it's running something behind. I'm adding the points. Yep, and so if we reload this, we can see the points, and I've been also able to give names to the wells. One is called well west and well east. Okay, so the rest of the information is repetitive. So we have now the super mesh, and from the super mesh, we need also the elevation. So we have 4 slices. We are using, again, invert distance. In one single file, which is called elevations, I have X, Y, and a column called ELE, and a column slice. So I can reuse the same file for multiple elevations. I'm adding 4 slices. Then I would also like to define some information about the problem class, as mentioned. So the problem class is flow this time, is steady, and is saturated. Saturated could be confined or unconfined. So this is a bit confusing, the terminology. If you know, in FEFLOW, we have this phreatic definition. So we can say, I would like to solve unconfined. The first slice is phreatic. The next ones are dependent. And the last one is fixed. So the whole information that you will see in the problem settings dialog in the graphical interface is basically here. Okay. What else? We can save the document, the super mesh, but let's also put some mesh information. So I'm gonna generate a mesh using triangle, do point refinement, gradations. The size of the points is 50 meters. Again, 5,000, but could be something else. We can also do a mesh smoothing if you would like. And to see the mesh and to see the elevation now, so let's save the FEM. And if we run this, so we are going to create a FEFLOW file with all the different elevation data. Okay, so this is, we can open, no, I was right. So here is FEM, and the file is this one. And if we extend the vertical acceleration, so we can see that we have in all the different slices, the elevation. And if we go to the problem class, is standard, steady. We define unconfined, the first phreatic, depending, and the last one is fixed. And like this, you can continue doing the different. So I'm gonna, because we are running really out of time, so I'll just do one thing to show you. So you are obviously able to put boundary conditions on all the rest of the information. So running this, and in parallel, I can tell you what is happening. So what I would like to put is in the south and in the north boundary, we have a constant head boundary condition. So again, you need to know the nodes and whether the nodes are belonging to a border. So there are methods for that. You can get a number of borders. So I have only one border. There are no inner borders. Then the nodes containing inside these borders. And basically I have a shed file of lines. I have a number of lines, and then I'm looking whether the point is in the line. And if the point is in the line, then it's a south or north boundary, and then set some boundary conditions. Then the rest is repetitive. We create multi-layer wells as well from the points that we have. And if we look the final file, we can run it. We can open the file, and then we can display the boundary conditions for the head. So we have now the heads, north and south. And if I do Control V, W, we have the two wells, and I define this as a multi-layer well with a constant flow rate, but could be also a different value. With this, I would like to, let's say, conclude the webinar. Thank you for participating. The next month, we will have another webinar related to a different topic of groundwater modeling with FEFLOW. Until the next time, and have a nice day. Bye.